Hello, physics students. This is Mrs. Crumschneider, and this is your concept development practice page 2-1, kind of going over this. So, little Nellie Newton wishes to be a gymnast and hangs from a variety of positions as shown. Since she is not accelerating, the net force on her is 0. That is, the sum of the forces equals 0. This means the upward pull on the ropes equals the downward pull of gravity. She weighs 300 newtons. Show the scale readings for each case, right? So the fact, remember, this is our equation for mechanical equilibrium. And this is that mechanical equilibrium because she's not moving. So if this little girl, right, her weight is 300 newtons. Okay? So if there's 300 newtons pulling down on her, that's that gravity pulling on her, then there has to be 300 newtons supporting her somehow, which is going to be coming from this rope that has the scale in it. So this scale is going to read 300 newtons. Because it's the only rope that is supporting her. Okay, so now we still have, right, that force of 300 newtons acting downward because it's still the same girl, but now we have two ropes that are supporting her. So each rope is only going to support half of her weight, okay, so 300 divided by 2 is 150 newtons in each rope. So this reading is going to be 150 newtons. All right, so now she's being silly and hanging upside down, but it's still 300 newtons acting down, right? So here we have 150 newtons in this rope and 150 newtons in this rope because, again, the sum of the forces has to be 0. Well, now I have 300 newtons, but I have 3 ropes here. So 300 newtons divided by the 3 ropes means that each rope has 100 newtons in it. So what is the scale going to read here? It's going to read 100 newtons because, again, she's not moving and the sum of the forces has to be equal to 0. So we have her being a kind of a smarty pants here and hanging with just one hand, right? And again, we know that her weight is 300 newtons. And there's only one rope here pulling up that has to be pulling up with 300 newtons. So this one rope, each of these has a value of 300 newtons, right? And again, they're not adding together here because they're just supporting her weight. And each scale here is independently going to support her weight. So it's 300 newtons on each of those. Here she is again, hanging around. This time, though, notice that she is supporting herself with her arm. So I know my sum of my forces has to be 300, but I have 2 supports here. And they're equal supports, so each one is 150 newtons. So she's supporting half of her weight with her arm. This scale here is going to read 150 newtons. Here she is again, hanging around. Ugh. She weighs 300 newtons. And again, there's only one rope here supporting her, so this has to be 300 newtons as well, so that the sum of the forces is 0. So this is going to read 300 newtons. Question 2. When Burl the painter stands in the exact middle of his staging, the left scale reads 600 newtons. Fill in the reading on the right scale. So this is sort of like this example up here, right? Where the girl was supported equally by the two different ropes. Same thing is happening here, right? And when we were up here, each rope had the same amount of tension or was supporting the same amount of weight. It was split equally. So when we come down here then, because he's standing in the middle, this has to be split equally. So this scale is also reading 600 newtons. So then this last question here says, the total weight of Burl in the staging must be. So remember, I have an upward force here on each side of 600 newtons. That means because he's not falling, that the sum of the forces down has to be equal to the total of these two together, which is 1200 newtons. And again, this is just like what we did with this girl here, right? Her weight was 300 newtons. She was supported by two ropes, so each rope was only supporting half of her weight. Same thing is happening here, okay? He and the staging here are supported by two ropes that are equal, have equal amounts of tension in them. And so if the sum of these forces up is 600 newtons, then the total of the force downward has to be 1200 newtons as well. So number 3, Burl stands farther from the left. Fill in the reading on the right scale. So again, we've already figured out what the mass of him and this staging is, right? It's 1200 newtons. And it's still going to be 1200 newtons even though he's dancing around here. So to figure out what this other one is, we're going to take our 1200 newtons and subtract the 400 newtons that we see the one rope is supporting, which leaves us with 800 newtons that have to be supported with the right rope. Number 4, in a silly mood, Burl dangles from the right end. Fill in the reading on the right scale. So again, we still know that our total weight of the painter Burl and the staging is 1200 newtons. Now this rope isn't supporting any of that weight, which means this rope over here must be supporting all of it. So this would be 1200 newtons. So these were all using that sum of the forces equals 0. Okay? And again, here we had a 400 newton force up, and here we had an 800 newton force up. Here we only have the 1200 newton force up, okay, on the right-hand side. So the second page of this, the equilibrium rule, the sum of the forces equals 0. Manuel weighs 1,000 newtons, and we see that drawn right here, and stands in the middle of a board that weighs 200 newtons, which we see right here. The ends of the board rest on bathroom scales. So there are our scales. We can assume the weight of the board acts at its center. Fill in the correct weight reading on each scale, right? So what's the sum of these forces going down? We have 1200 newtons total, correct? So, and this is equally supported. So this scale is going to read 600 newtons, and this scale is going to read 600 newtons. So it's the same idea as what we saw with the ropes hanging, but now we're talking about it with balances or scales like you would use in your bathroom. So number 2 says, when Manuel moves to the left as shown, the scale closest to him reads 850 newtons. Fill in the weight for the far scale. So again, the sum of our forces going down is still 1200 newtons. But now we know we have one scale supporting 850 newtons. So figure out what the other scale is supporting. We're going to take our 1200 and subtract that 850, which leaves us 350 newtons here. again, because the sum of the forces, because the manual's not moving, the board's not moving, the scales aren't moving, right? Nothing here is moving, so it's in mechanical equilibrium, which means that the sum of the forces downward, which is 1200 newtons, has to equal the sum of the forces upward. So if this one's 850, this one has to be 350. Question 3. A 12-ton truck is 1/4 the way across a bridge that supports 20 tons. So we see the bridge weight here, okay, and we see the truck here. A 13-ton force supports the right side of the bridge as shown. So we have 13 tons over here. How much support force is on the left side? So again, because this is not moving, the sum of our forces has to be equal to 0. So the total of our downward forces, which is 32 tons down, has to equal 32 tons up. Now, we know one side is 13 tons, so to figure out the other side, we're going to do 32 minus 13, which leaves us with 19 tons. So the other side is supporting 19 tons of this weight. Number 4, a 1,000 Newton crate resting on a surface is connected to a 500 Newton block through a frictionless pulley as shown. So let's fill in a little bit of this, right? They told us that this crate has a weight of 1,000 newtons, so that's just coming from there. And they told us the weight of this iron block is 500 newtons. So that's where those numbers come from. Friction between the crate and the surface is enough to keep the system at rest. Okay, so again, this is at rest, which means we are in mechanical equilibrium. So the sum of the forces has to be equal to 0. The arrows show the forces that act on the crate and the block. Fill in the magnitude or the size of each force. So here, right, our block is pulling down with 500 newtons, and it's not moving, so I have to have an upward force of 500 newtons. So the tension in this rope is going to be 500 newtons. Here, I have 1,000 newtons acting down, which means I have to have this table supporting that weight with 1,000 newtons up. So that's that normal force. Now, the tension in the rope isn't going to change. So my tension in my rope here is 500 newtons, which means my tension in my rope here is also 500 newtons. Now, that tension, right, is acting to the right. The force that's opposite that is this friction force acting to the left. And again, because they're not moving, these have to be equal in magnitude or equal in size and opposite in direction. So this friction force is 500 newtons. Number 5, if the crate block in the preceding question moves at constant speed, the tension in the rope, okay, is the same. So the tension's not going to stay or change. The sliding system then is in what is called a dynamic equilibrium. So the difference between these terms, static means not moving. Dynamic means moving. So up here, okay, when we were talking about manual, standing still, this is a static equilibrium because nothing is moving. But down here, what we just talked about, it told us that if the crate and the block start to move at a constant speed, okay? In a constant direction, now it's moving, and so it would be called a dynamic equilibrium. So, for example, you've heard the word static before with electricity. It's called static electricity because that electricity is not moving, and that's why it's called static electricity. In science, static always means not moving, and in science, dynamic always means moving. So that is your concept development practice page. If you did this together, then you have, or with me, then you have this all done, and you just have to take pictures of it to submit and turn in for the assignment. So you just have to take a picture of the 2 pages, or use that Adobe Scan app to scan those 2 pages and submit it for the assignment in Google Classroom. Thank you. I will talk to you tomorrow. Have a great day.